Hey everybody, this is Larry. This is day 14 of the August Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this really tricky problem, remove boxes. So I actually really recommend watching my video on 2x. Not right now, but I'll do the explanation first. As you can see from the runtime that this is a very long video, but actually, to be frank, I actually didn't spend that much time on it. It's just that I spent a lot of the time thinking there's an n cube algorithm, but it turns out that the optimal algorithm is n to the fourth. So, and I actually had an n to the fourth algorithm very quickly. So maybe not that quickly, but I did stumble across different ways of doing it. So definitely watch that. First of all, I am doing this explanation live, so it's a little bit slow. Fast forward, do whatever you need to do. I am going to do this explanation now, but I do actually, like I said, I think I did not remember this problem enough, as you can see, because it took me 90 minutes to do it. But so at least in the first 20 minutes or so, you can kind of see my thought process about this problem and kind of getting it from dynamic programming and kind of get it through. So I definitely recommend watching that. And for this one, I would also say that if you don't get this one, it's okay. Work on other dynamic programming problems first. So my explanation is going to assume that you have a good working knowledge of dynamic programming. And for me, yeah, the first thing that I would think about is, yeah, and it's gonna be a little bit too tricky for interviews, and also it's very one-off. Even though it doesn't feel that way. Some of that is, as I said, because I thought that n to the fourth may be too slow, but it turns out to be fast enough. If that was the case, I actually would have gotten it much earlier. But that said, you can kind of watch my video to see what I did. But anyway, yeah, so for this one, the first thing that I notice is, and you can watch this in the video, is that there's going to be n square, or like I diagnosed the n cube solution very quickly. But the thing about these dynamic programming problems is trying to do it in a way such that you're effectively doing a brute force, but in a smart way. But yeah. In this problem, because it became a long video, so I used this thing called LRU cache. I do, as I say, this is only for people who are more experts in dynamic programming. So if you don't know why you're using LRU cache or cache, don't use it. Especially because in an interview, you're going to be asked to explain the complexity and stuff like that, and you're not going to be able to, then that's going to be a little bit tricky. Also, this is no longer needed because I thought I could do an optimization bit. So let me actually clean this up a little bit. But yeah, so this is the code, but the idea is that, okay, so for this goal, we have in a subarray, we want to solve the problem of the sub array of boxes, a sequence of boxes where count is the number of consecutive boxes in the thing. So I think I said this in the other video as well, is that the idea here is that this is an asymmetric kind of problem in how you handle it. And what I mean by that is that, for example, let's say you have this sequence. The way that you may think about is, okay, let's think about the next move and then do a recursion. For example, let's say our next move is 2, and then now we do a recursion. Except for the overlapping segments, because if you kind of think about this thing, say, you may want to do this. You want to remove this chunk and then this chunk or something like that, and then they overlap, right? So we want to think about how to do the segments in a way such that they don't overlap. And in that, sometimes it makes more sense to figure out the last thing that you remove. And in this case, the last thing that we were going to remove is some combination of ones. And I think I had a good case. Yeah, I think the good case is something like this, where basically the case is something like this, and I think I have maybe even additional ones here. But the idea is that, okay, So the optimal move here is actually to remove this one first, and then this sequence of twos, and then now you have this one that pairs up with this one, and maybe just keep it this way, because the ideal move here is to remove the one, and then remove the twos, and then the one will pair up at the end. So now you're out of the way. To brute force that is saying, okay, now let's keep track of the consecutive number of ones per box. And I think this is very hard to kind of conceptualize, and I only got it during the live solve because I kind of had experience with this. Otherwise, this is very hard. But basically here, then let's say that that's the case. Well, we start off the base case by going, okay, we want the entire input where there's 0 consecutive numbers. Then here the base case is, if we have one number left, then, and we assume that this number matches the current count, so that means that the score would be count plus 1 times count plus 1. So here, if we have no boxes, then we return 0. Let's say we just want to end the series, then that means that now we want to take we consume the current box or box sub left. We consume that, and we have this score of count plus 1 square, and here we just take the rest of the suffix, right? Otherwise, we go through it, and we go for each box, because the thing is that, okay, I removed the test case for some reason. Let's say we have something like this, right? You can keep on constructing a case such that you basically have another symmetry here. Let's just use threes though. Where the ones that you care about is this one. Your last move may be something like this, this, and this, where we skip this one and skip this one, right? So for each one, we ask ourselves, we have two choices. We can either partition this here, or we don't partition this, right? So here we can say, okay, we partition or we don't partition. Here we partition or we don't partition, and so forth. Here, if we do partition, then we basically partition the left, and this is, if we do partition, then everything here, we put it in one chunk, and in that case, you have a one of 0, and then you increment the number of count to the right, and you move the index along, because here, we use the same box, but now we're looking at a sub-problem of this sub-problem, where the box is this box plus 1. So what I will say here is that I'm not going to do a good job of explaining this, because I'm a little bit tired, because I am recording this after working on this for 2 hours. But I would say, maybe you can watch another video that has a better explanation. It's fine. The reason why I say that is because the reason why I recorded these videos my way is because I think that what's unique about my video is my thought process, and that you get to see a regular dude kind of attack a problem and kind of struggle through it and kind of stumble through the answer my own way, right? Because there are probably 20 videos out there on remove boxes, and some of them are going to be good. My goal is not to create the 21st good video of remove boxes. My idea is kind of create a new, different thing where you're like, okay, Larry is solving this problem. Let's see where he stumbles on, how he fixes, like he gets stuck, and then I fix it while I'm getting stuck, right? So for that reason, I urge you to kind of watch my video on like 1.5x or something like that next. But I'm going to skip a little bit, because also, to be honest, I'm a little bit tired today, because I spent like 2 hours on this problem. So So definitely watch enough of that. I think don't mind, but I would also say that the only reason why the video was so long was because I thought there's an n cube solution. I did figure out the n to the fourth solution maybe pretty quickly, especially if you're watching on fast forward or if you skip ahead. So yeah, for this problem, just for quick complexity's sake, is that here for the left, we have left input can go from 0 to n, right can go from 0 to n, count can go from 0 to n. So you have n cube possible inputs. And for each input, we have O of n time because of this for loop. So it's going to take O of n to the fourth time. For each of the input, we have O of 1 space. So it's going to take O of n cube space, and that's fine. So this is going to be O of n to the fourth time and O of n cube space. Sorry if this video is a little bit weird. Let me know what you think. This was hard. So yeah. So watch what I. Now watch what I did live. But I hope that sets up the context. And yeah, and that's okay. Hey everybody, this is Larry. This is day 14 of the August Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Today's problem is going to be remove boxes. Oh boy, this seems like it's going to be one of those traditional n cube dynamic programming ones. Let's see if that's actually the case. Hit the like button, hit the subscribe. Wait, did I say that already? Probably. But yeah, I usually solve these live, so if it's a little bit slow or hard, fast forward or maybe just ask questions. Do what you need to do. Yeah. Day 501, let's go. Okay, so you're given boxes, different colors. Each time you choose some contained boxes of the same color, remove them and get k times k points. Remove the maximum points you can get. So I'm not gonna lie, this is exactly the type of dynamic program problem that I'm really awful at. It's gonna be n cubed in some way, so because you have n squared states and then some way of divide and conquering left and right and then merge them together. The tricky part about this, and I know I'm hand wavy a little bit, but I would also say that if you are struggling with dynamic programming, maybe try another problem first because this is non-trivial and I struggle with it a bit, to be frank. And then the other thing is that what is the other thing? Yeah, so there's going to be n squared states, left, right, and then maybe a O of n loop that is what makes it n cube. And this is just me guessing because from experience, I probably have done this problem, but I still struggle with it because it just doesn't come up that much. And also they're always like, it requires you to think backwards, right? So the intuitive thing to think about is, okay, given these things, what is what is the first move that you do, right? And the first move, you're just like playing around with the problem, and you should explore the problem a little bit. The first move you may say is like, okay, let's point out, let's remove 2s and then see what happens, and then you get 3. You have these things, and you move a 4 and then 3 and so forth, right? But the thing that I've known, and this is where I'm going to get or try to practice, is that you have to think about some of these problems or be able to think about some of these problems backwards, meaning that, okay, you start at the end and then what happens when you kind of go backwards, right? So that's basically what we're going to do here. Yeah, just start at the end and then go backwards, and then you have some scoring function. Yeah. And then it becomes a question of, and this is going to be a little bit tricky to explain. So if this is going to be a little bit of a sad video, I apologize in advance because this is something that I struggle with as well. So I may not explain it very well. And people always ask me why I don't, just go over the perfect explanation. Just to give you a little bit of reasoning. The reason is because I want to show people how someone who may or may not be good solve these problems live and what their thought process is as well. They're like, if you Google this problem or you search on YouTube or whatever, there are probably like 20 different videos on this problem, and maybe they even just go over the perfect solution, right? And to me, that's fine. It's just not, I don't need to be the 21st video explaining how the perfect solution is. So that's why I do it this way, so that it gives you a little bit of a different perspective. And if it's a little bit long, then you know that it's okay that someone struggles as well, and so forth. But my question is, okay, I think I have an idea though, now that I'm talking through it a little bit. As we said, we know that this is going to be, you know, something like this, right? Where, so basically we have the sub array of boxes inclusive left, right, left, remaining, maybe that's a better word for less confusion. What is the best score? And I'm gonna name it go, because I mean you can name it like best score or something like that. It doesn't, like, to me it's almost just as bad as a function name, so it doesn't really matter. I'm gonna do the memorization later. Maybe I forget, but which sometimes happens, but we'll see. Anyway, so okay, so what happens if left is equal to right? Then we have one box. So yeah, if left is equal to right, then we have one box. So then we just return one, right? Okay. And something that I'm thinking about right now is, okay, so given a bound of subarray of boxes, you know, and I skipped ahead a little bit, we can go over why this is the case instead of recursioning on like a subarray, but this is basically how you represent a subarray. Again, this is a little bit skippy or heady, so if you, but that is like a core principle of dynamic programming, or a very common pattern, if you will, on dynamic programming. So again, practice easier problems if that isn't, you don't know how I got to just use the indexes here. But then here, now let's say we have, let me just copy this over a little bit just for visualization. Let's say we have our left is here and our right is here, right? As we said, we do want to think about this backwards, being like, okay, now we only have this array. What is the last thing that we're doing? Well, the last thing, you can enumerate things in different ways, as long as you do it in a way that considers every possibility, right? And for me, at least to kind of keep the recursion consistent in a way, and because we cannot go outside the box for a reason that we will probably visit later, if we are all forced to do this, then one thing that we can do is just look at the first cell, and then also there is we look at the first cell and then go, okay, what happens if we use this first box, or okay, because then what's the possibilities, right? The possibilities are, okay, so yeah, let's print this array here. I say okay a lot, and I say a lot. I need to get rid of some filter words, but yeah, so let's say this is the box we're considering. If we ought to remove the last thing, then we have to remove one of the boundaries, right? Otherwise there's no recursion, because that's I mean, maybe not strictly speaking, but you can also say that, okay, so what I said was probably a poor reasoning, but the reason why we can do this is that if we remove something in the middle, let's say for whatever reason, we remove these things in the middle first, but that's equivalent, because in this problem, the order doesn't matter per se. Yeah, because the order doesn't matter. If we are given, let's say the optimal way to remove stuff is kind of these three segments. What we're saying is that, okay, let's say the optimal way is to remove this this thing first, this chunk first, then we can remove this. Well, that's equivalent of just removing this first and then removing this, right? Actually, I don't know if this is a valid removal, because I don't know if you're forced to remove all the boxes of the same color, or you can kind of separate them out. It doesn't actually matter in this case because of k times k point scoring, because of the scoring is quadratic. You always want to be greedy in that way. That's another thing that I'm not going to prove, and it doesn't matter because we're going to go through it. But in that case, I hope that makes sense, is that, okay, maybe a better example is, okay, let's just say we have, you know, this is the optimal solution, which I think it is because just by looking at it. Oh wait, no, I think the optimal solution is actually doing the 4 and then, well, and then in a recursive way doing the left and right. But in that case, it doesn't matter which order you go. I think that's my point, is more that it doesn't matter which order you go. And also, the other thing that I was going to say is that there is some symmetry here, meaning that it doesn't matter whether you go from left to right or right to left in this case, because again, because the order doesn't matter. As long, like if you have an optimal partitioning, the order doesn't matter. So therefore, we force an order because it doesn't. As long as you do it in a way such that every possibility gets checked, then that's okay. So let's just say. Then in this case, we start with just removing one cell. So let's just initiate best to that. I mean, you could also do something like this, +1 right, +1 right. So this is, you know, obviously this is going to be bigger than that, so we can just remove this. This is just us removing the first box by itself. Okay, and then now as the last move, and this I think is a tricky part, but maybe I am a little bit more practiced than I did when I first getting back into it, which is that, okay, let's say, is this a color or color? Okay, let's say our last removal is of boxes of this color, right? Then what does that mean, right? So that means that in this case, well, this is not a good example, but let's just say we add a, I don't know, 3, 5 in here, right? That means that, okay, our last boxes can actually go through the entire span, right? So our last span could be this, which is just 1, 2, which we already did, or it could be 2 2s, or it could be these 2 2s and this 2 right here, right? And what does that mean? That means that when we do the recursion, this is going to be its own sub segment. That means that we move them individually earlier, and also we remove these things individually earlier. Okay, so that's basically maybe, not gonna lie, that's gonna take a little bit of a leap of faith. I'm gonna continue a little bit because it's kind of hard for me to explain this. So let me know what you think. But basically, okay. So let's just do a running score maybe. So basically now what I'm doing here is that, okay, let's just say we want to calculate what do I have this for, right? This is so that if let's say we remove 2's last, then that means that we have to remove other stuff first, which we do a recursion on. That means that we have to remove the 5 and the 3, and then the 1 by itself, and then the 3, 5, and 3 and the 5, and then the 3, 4, 3, right? So those are the things that are kind of partitioned by our 2's. So in that case, we just want to get the sum of, let's say we want to make our last move these 3 2's, then we have to get the score behind here, and the running score just lets us keep track of that. Hopefully you'll see that pretty soon as I kind of do it. Oops. So yeah, so now let's just say for index is in range of, let's see, let's just say left +1. We want to go over this inclusively maybe. Yeah, okay. We might have to think, I have to think about the indexing here, because if it's inclusive, okay, that should be okay. But now it just means that if left is greater than right, we return 0. We had that base case. Yeah, and okay, so that means that, okay, we want to keep track of last boundary as well, is equal to so yeah, this is a lot of indexing, but I just have to keep track. So let's say this is the thing. Oh wait, so we have to just keep track of the last 2, which starts at left. Okay. So then now we want to calculate the score of the thing that's in between. So running score, we increment this. Oh wait, this is only if this is a 2, or this is the same color as the first one. So if boxes of index is equal to boxes of left, then we do this thing where running score, we increment it by goal of, and to be frank, everything I said could be wrong. Like I said, I'm not very strong on this, so we'll see where I go with this. But yeah, so this is basically the last boundary plus 1, because this is going to be inclusive of left plus 1, and then we want to be index of -1, because again, these are inclusive bounds. So we want to, for example, if we have these two 2's, then we want to consider these two boundaries, right? So it's this, and let's just do also count is equal to 1. This is basically the number of boxes that we're using so far. We want to increment boxes by 1, and then we want to set last boundary to so now index is the last boundary, so we set last boundary, or maybe last same box, maybe it's a little bit better, but we set this to index for that reason. But then now, of course, the current score, but the best score so what is the scoring function, right? So this is just the running score, so the running score plus this count square thing, which is kind of what we have here, the count square thing. So the current is going to be this plus count square plus goal of index plus 1 to the right, because basically this is the auto partition. So basically, for example, if this is left, abbreviated with L, if this is the index, which is I, and this is R, then basically the running score gives us everything in between. So let's actually move this in a little bit. The running score will give us the sum of this plus this, ... and the count will give us the score removing the 2's, which are all these things. And then this thing is just the score that you get for the rest of the components, right? The rest of the subarray. So this is a possible score, and we basically take the max of this and the current score. And then at the very end, we just return best. I think this should be good, maybe, or close to it. Am I missing any cases? Maybe, definitely very possible. At the very end, we just go from 0 and -1 for inclusiveness, and this is going to be n is equal to length of boxes, obviously. So yeah, so we didn't do the memorization yet. I know, don't worry about it yet. We'll just take a look to see if this is right, and then yeah, for smaller things you don't. This is just brute force, and then now we'll try maybe some randomly generated, and by random I mean I'm banging on a random thing on my thing, and then kind of see. Hopefully this is all right. All right, this looks good. I mean, am I super confident? It's very easy to have off by 1, as we talked about, so maybe not. But for the purpose of speeding ahead, I'm just gonna get this in there. Oops. But yeah, for memorization, right? So what are the number of possible inputs? Well, left could be from 0 to n inclusive, actually n minus 1 inclusive, and right can be 0 to n minus 1 inclusive. So this is going to be all of n squared possible inputs, or sometimes refers to states. There are more nuances than that, but I'm just skipping ahead a little bit. And for each one, we do all of one space because we want to store it down, and we can store it down in a linear way. So let's do that. So here we have two things. I always try to write it this way. Let me actually put these comments closer to here. But yeah, so we have cache is equal to, doesn't really matter, but for this is just an n by n array, and then you have has cache is equal to the boolean of the same thing. I don't know why I wrote boolean, but I think because I was saying boolean. So then now the caching becomes a little bit easier, because then it's just if has cache of left right, then return cache of left right. And then at the very end we want to set the cache, which is that's the way that I like thinking about it, because because it's just way more easier to think about, right? Because you just get the result, you cache it later, and yeah. I probably could have tested a big one first. Hang on. Oops. As well. Oh, maybe that's more than 100. Actually, I didn't check. Oh yeah, what got 180? Whoopsie daisies. Is this 100? This is probably less than 100, but that's fine. It's big enough that it should time out if it isn't fast, and we can test that by saying that we don't cache it. Will this time out? It should. It should be big enough to time out. We'll see. Yeah. So basically, it should time out, and our cache is working as expected. So let's give it a submit after this thing finally gives us the answer, gives us a status, and then we of course correct it and make sure that we run the code really quick again. Okay. So let's give it a submit. Possibly missing some cases, but that's okay. Ooh, wrong answer. Dong dong dong. What am I getting wrong here? That's a little bit awkward. Let's see. Like I said, there could be an off by 1. So what happens if this is on the right? So that's a little bit awkward, a little bit sad, but at least we're close. I think like I think I'm just missing some weird thing. Let's see. Running score should be okay. This is right, but am I doing this right? Yeah, we definitely want to consider all of it. Would that give me a wrong answer? I hope so. Nope. That's annoying. And this is basically like it's probably way tough to figure out. Like this is a hard problem to debug for this, or at least this case is way hard to debug. Oh. No, that's right. I think. Because this is... Okay. So I'm very close, but... so I'm just checking my stuff. My base case should be right because this is inclusive. Dong dong dong. This should be good. Removing the first box by itself. I think maybe. So what I was going to say that is that maybe maybe we didn't look at the constraints enough in that you're forced to remove the same color boxes. Like so you cannot remove just like in this case you cannot remove 1 2 by itself. You have to remove 2 2s. But in that case. That would only be the case but we know that that's not one of the reasons why it's wrong, because if that's the case, we would have the wrong answer because we followed that logic through. Having that restriction means that our output would be better than the best possible answer. But because this is lower than the best possible answer, it means that we're not exhaustive in a way. So there may be an edge case that I didn't consider or something like that. Because if we did, then we would have like so there maybe a little bit, but generally, if your answer is better than the best possible answer, that means that you didn't respect some restrictions. And if it's lower, I mean, it's still maybe the case that you didn't respect some restrictions, but for this particular test case, it means that you didn't consider enough cases, because that means that there is a way to break this such that I didn't split it apart. So there, yikes, this is kind of tricky to debug because there's just a lot of boundary conditions. I do think that I am off by 1 here somewhere, but yeah, but I'm not quite see it. I don't see it innately. Because if the index, so this is inclusive, and if this is right, Then let's see what happens if I do this. Okay, so this is what I would expect, is that I just get a really low answer. So this part is right, or at least not as wrong as it could be. But then why am I getting this wrong? Dun dun dun. And order 1 seems okay. Or we get the one where we get order 1s. So one thing that I would try to do is just see if I can construct a easier to explain wrong answer. And sometimes I do that by creating my own, or sometimes I take this but take a similar subportion of it. But this is just 1s and 2s, so this is essentially the same idea. Alright, maybe take half of this and then figure out if this would give us. So what I'm looking for is having a wrong answer that we can debug from. So this is good in that now we have a simpler case that is wrong. But why? Dun dun dun. Because basically what I'm trying to do is maybe get a case such that I can do I can manually try to figure out the answer and then look at my code, what does my code actually does, try to figure out the discrepancy and then handle it a little bit better. Okay. This is going to be a little bit tiring. Yeah. Huh. Oh, okay. Maybe I was wrong about one of the symmetry things. I think I could be a little bit more exhaustive, but so some combination of this weirdness is enabling a wrong answer. Yeah, right now I'm in debugging mode, so I'm not really talking that much because as you can see what I'm doing, which is that I'm really experimenting with things in general, with kind of getting a simpler case. I think I'm getting close though. So, because we know that this is the wrong answer still. Let me think. Yeah. Okay. I think maybe one of my assumptions is wrong. I think it's something like this. I don't know if I could remove that part, but where no, okay. But I think it's something where I try to remove the 1 with the 1 instead of just the 1. If I just remove the 1, then I could be okay. And I think I was wrong in my assumptions that about what I said about the segments. So so then the question is, how can I remove this 1 by itself? At least in a way that is consistent. So I was wrong about some parts of the because the idea here then is that I think I was wrong. I thought that it would be exhaustive, but I was wrong. So I have to kind of modify this a little bit. But the idea about this test case that makes it wrong is that, okay, you have this. I think the optimal move is to remove this 1, and then everything will fall in place first. But what I did, what my code does is try to remove this 1 with this 1, and then separate out the twos, and that. Yeah, and I think that may be the reason why. So I have to be able to remove this 1 by itself. And how I would do that is kind of consider actually just removing the 2's. So we have to figure out how to remove the 2's by itself, but we keeping the 1. So the way that my initial thought was that I could, if I backtrack how I think about this, is that if we want to remove the 2's, say all the 2's here, yeah, then I would remove the 1's, this 1, and then by removing this 1, I could remove all the 2's altogether. But it turns out that that's not the case, in the sense that we actually don't want to remove this 1. We just want to remove this 1 so that we can remove these 2's, and then now at the very end we have this 1 and matching this 1 together. Let me think about how to exhaustively do this in a smart way. So how did I just remove this 1 in the middle? Well, the thing is that you would not remove the 1 in the middle. Well, the alternative way of saying that is that you would remove the 2 first. And I do know how to implement this such that we can do it in an exhaustive way, but it's just the coding is going to be messy. So I'm just trying to think whether there's another cleaner way of doing this without making the complexity way crazier. Because basically, in this scenario, actually, the last move that we want to do is going to be this one with this one, but maybe without, either with or without some of these internal ones. And I don't know if that's just an edge case, because that's the other thing I'm thinking about is this an edge case? Huh. What if we want this one? Or we want to keep this one because this is a 3, right? Then we want to do what the last move could be, yeah, after this is done and this is done, we have 3 1's left. So we cannot just assume that we will do the 2 1's and then do the middle. So okay. How do we do that? Maybe my running score is incorrect. No, man. That's what you, maybe I tried to be too clever. So right now I'm just thinking about the recursive divisions and whether there's a smarter way of handling it. And maybe I don't know how to solve this one as a result, because this is going to be a case that haunts me as well. Maybe it gets it right now, but it's going to be a future problem. Okay, so even then this is wrong, which is kind of good, I guess, but well, that's going to be a struggle. Did not consider this case where we have to remove an internal 1. Well, that means that there's another property that maybe we can figure out how to subdivide. I mean, this is going to be, like, I'm relatively sure that this is that kind of divide and conquer, but because even if you do going from the right to left, you have this one and this one, you would separate these components, and that's not what you want to do, because in a reverse thing you just do this and then this part. So you actually want this one, and this one to be your last move. And in that case, but not this one. How do I do that in an exhaustive way, in a clear way, right? And also another thing that you can imagine is that there's another, this thing here, say. So that now you cannot just like, you cannot do the naive n cube thing. You have to separate out this thing because you don't care about this thing, and then you want to separate out these things, right? So, and you can also even like play around with a case where you have this in the middle, so that now you have to get rid of this one, but not, you want to keep this one. So yeah, right. So there are definitely more constructed cases that I had to think about, but I was wrong. Okay. Yeah, I mean, this should give me a wrong answer. If it's the right answer, just by luck. Oops, I guess I have to put it here more than the other voice. So how do I do this? Yeah. How do I? Because I did have an assumption that on the greedy, maybe, where if these are the same color boxes, then we can always partition the middle. But I guess maybe that's not the case. But if that's not the case, we can't really do it in an exhaustive way, in a reasonable way. So how do we care about only this one? I think this one and this one and this one at the very end. Can we think about this backwards, in a merging kind of way? No, because there's no way to divide this into two components, right? Because this answer requires 4 partitions, or 1, 2, 3 partitions and 4 things, and you can't really separate it out without the score function. Well, at least not without another state. I guess that's the other thing. Maybe I was too stuck on thinking about it like this. What I should do is add another state, which is the number of running count, then we can do it. Okay, fine. Oh man, this is such an annoying file. Okay, I got it. Okay, so then, okay. Yeah, so basically here we want to add another state. So we have to kind of, okay, let's change this for now, though I guess this is, these parts is true. Okay, so now we want to, so this is the definition so far, and also we have maybe a sort of count so far. This count is actually exactly the same as this count. But then now we have 2 states, right? Of, okay, it's the same thing, which is that now we're running here, and we can either include this or not include this. So let's do the math both ways, and then we could play around with it. I don't know if I don't know if all these make sense anymore. So let's remove this. Doesn't make sense. Remove the first box by itself. So this is going to be removed, and then this is going to be 0 as the new count. Okay, let's say our last remove is the thing. So now let's re-loop the middle. If the boxes are the same, then we have 2 choices. We can either remove this box last, or it gets swallowed up in the middle. So what I mean here, right? That means that, for example, if I had this thing, that means that if I have this thing and my index is here, we can choose either to include this in or not inside this box, right? Or inside the current thing that we remove. So what does that look like? If we remove this, well, right now it's n to the 4th, so we have to figure it out a little bit first. But before we try to figure out how to be better, going to figure out before we try to figure out better, let's get correctness first. So, okay. So yeah, so let's say we had this one. Right. So we have two things. One is, okay, so if we use this box, we can continue the chain. Oh, well, even if we don't use the box, we can continue the chain. So let's think about this. Okay. If we use this box, what does that mean? If we use this box, then we just have this thing. And I think this actually is basically right. I mean, some of these states are a little bit weird now, but let me think about this. Okay, we have one box left, or we have no box left, and this is count. Oops. Times count. Count plus 1 times count. Wait, how do we? Oh, this is the number of current. Count is the number of current run with the same boxes as boxes of left. Something like that. So then this is going to be count plus 1. And in this case, we just do count times count. Okay, then in this case, we don't actually need the plus 1 because the count is summed up. Okay. And then here, we don't need this. Okay. So then now let's go back again. Okay, what happens if we keep the box? If we keep the box, then we do this. Well, we don't need the running score anymore. We can just... Wait, do we? Well, we could do a recursion. So the recursion here, if we use the box, okay. If we use the box, then we do go of left plus 1, index minus 1, count plus 1. It's going to be the score. Yeah, okay. If we don't use the box, what is the score? Then best is equal to max of this. We go left plus 1. Well, we don't use the box, then we just ignore it. Yeah, if we don't use the box, then we just ignore it. Okay. That makes sense because then, and we'll get to the next one before we use it, right? So this is this. This is the left part, and I didn't do it, but we have to do the right part as well. So this is index plus 1, right? And this is 0 maybe? I'm not sure about this 0. Maybe it's 1. but I think this is wrong. Should be plus count times count. When this is just and this is not removing. It's end the series here. Because if we basically end our removal at this current point, this is going to be the thing, right? And then we have to add the score as well. Okay. We don't need the boundary anymore. So if we don't use the box now, do we just ignore it? Yeah, because by definition, if we do use the box, then we will have this partition. So then we shouldn't need to know this. Okay. Well, this cache thing it's weird. So let's remove it for now, and then let's take a look. It may time out actually. So okay. I'll do the thing the other way in a bit, but let me just cache this for now. It may still time out, to be honest, because this is n cube or something right now, maybe, or n to the fourth. Sorry, but I just want to see for correctness. This object not callable. 19. What? List object not callable. What does that mean? I don't have a list object, do I? Oh, I see. Because I called this cache. Whoops. Okay, fine. Okay, so this is drastically wrong, so I'm a little bit off here. But, why am I off by so weird, though? Or at least, like, given this case. Are my states really wrong? Maybe. Oh, this is wrong. No, this is to the... Oh, I messed up this. No. I messed up this. This should be 0. Where this should be... This should be 0 as well. No, wait, what am I doing? This is really weird. That's why. I don't understand what I'm doing here, which is probably why it is as well. So this is the right side, and this is the left side. The left side is left plus 1 index minus 1. This should be just 0. And then here is the... This part doesn't make sense for the right side. So the right side of using the box is that we... Okay, this actually goes to index, and then we do count plus 1. Okay. Man, I don't know what I was thinking when I typed that. That was just very weird. Again, this may time limited because this is n to the 4th right now, but I'm just hoping to at least kind of see if I'm on the right track. I think these are the right answers for these, but let's remove the big case for now. So we're going for correctness, and then we could kind of figure out how to condense this. So this looks good now, more confident about it, and then now I can figure out how to reduce this. Because right now we do this for loop thing, which is why it's so slow, but can we do without the for loop? So, how do we do this in a way with our for loop? How do we do compress this path into something easier? Huh. Can look at. Wouldn't really work. Let me think about this. So this is n to the 4th right now. Can I? There probably is a way to compress this to be better. What if we don't? We don't, then we go to the next one. Yeah, I don't know. Yeah, this is hard. Oh, did I not have a thing? Is that why? Wait, I thought I had a thing. Okay, so this is actually fast enough. What's 100 times? I guess 100 to the 4th is fast enough, but I don't know. 100 to the 4th is 100 million, which for if I'm not using Python may be fast enough. Let me just actually construct a case. I don't know if this is the worst case though. So we'll see. It runs, but very slowly. I think on a faster language, this is not that much of a concern. But I don't think this is going to be fast enough. So how do we optimize this to n to the cube? Can we optimize this to n to the cube? If we end the series there, that's good. If we don't, then what do we do? Well, then we continue to find the next point. But I'm trying to think whether I can think about this in terms of, like if we do use it, then what does it look like? Well, we do, or we don't use it, then what does it look like? I don't know how to do it without thinking about a box, because then now we could compress stuff. Then can we do something like go of index right count? So that's what not doing it means, right? This is the equivalent of this for loop. So then now once we do this, the rest of the for loop, this is equivalent of the rest of the for loop, and then that means that we can return best, say. So this is much faster. And then that means that, I mean, and then the other case is going to be just like awkwardness. Maybe. I don't know. This may be fast enough by itself, to be honest, but I'm not sure. 12. But let's do one more optimization. 12, 24, 40, 36, 48. 96 is close enough. So maybe it is fast. Ooh, but this is wrong. Dong dong dong. Also, this is wrong. Okay. At a certain so is this right? I forget if this is right anymore. No, this is going to take a long time. This is the part where I wish I have my computer, because then like I'm doing it locally, because then I could at least get the answer, even though okay, so this is still wrong for some reason. Actually, I even got this wrong. This big one. That's weird. I actually thought this was right because I was focusing on these, but then it turns out that this is actually still wrong. So before I make this optimization, I have to figure out why this is wrong. So I'm off by a little bit. I think maybe this means that this only comes up. Yeah, maybe this doesn't come up anymore. I don't know if that's enough to do it. Yikes. Wait, is my answer better? No, my answer is lower. So I think I'm missing a case here where ending the series here is a little bit different, because that means that maybe this constant is wrong. Maybe I need to start this at 1 so that we can end the series properly. I think maybe that's why. Nope, now I'm wrong on a lot of things. But I think that is why, though. I'm not. I think this one is giving me the wrong answer. Ending the series here. Maybe this is count plus 1. Because if we started off 0 and we ended here using this left, then I think maybe that's why. Now I'm just like guessing a little bit, to be frank, but looks good. So then now we can add this thing back in as an optimizer, and okay, so that looks good. And then that means that now instead of this for loop, we can optimize this array to have a pointer that goes from, for every boxes of whatever we, now we could just figure out what the next boundary is, and then we do this divide, right? And we can do that by just pre-calculating that. Okay. Let's just say the next, what's it called? Center? No. Processor. What is the word? Processor. Whatever. Let's just go with next. I think next is the keyword though. So yeah, for each thing, we want the next cell. So it's gonna be just this times n times n, and basically this is the next index that contains the same value. And then here we do something like for we'll do it backwards, I guess. one. Let's do previous is equal to so yeah, okay. But this is looking backwards. So previous of boxes of index is equal to index. But before that, if boxes of index is in previous, then next of index is equal to previous of boxes of index. Okay. And then now, so instead of this loop, we can skip straight ahead to if next of boxes of index is not -1, then we basically do this is left. Otherwise, index is equal to the next of boxes of left, and then now we have this thing. And then we don't have to return best here, but yeah. Okay, let's take a look. Oh, whoops! This is not an if statement. Oh, maximum recursion. Did I mess up somewhere? Probably on this thing. Huh. I don't know. I don't get it. Okay. I don't see anything obviously incorrect. Though I've been saying that or problems. So, yeah. Okay. Let's just print out this. Okay, so 1 is -1, -1, -1. This is 7, which seems good. -1. This is 4. 0, 1, 2, 3, 4. Yep. 3. This is 5, which seems right. This is 8. Okay. I mean, this looks okay on so I don't. So that part looks good. What happened here? Left, right, index. Apparently I'm doing something where the index is weird. Oh, did I miss something? Because now it is left, right, and the index is what? Dun dun dun. Why would we? The index is 4. Oh. Oh, this is. I am dumb. Okay, fine. Well, this is -1, so actually I have to fix this as well. But I think this should be good now, maybe. I mean, better. I don't know if it's good. Okay. But now I have way wrong answers. Like this one, which doesn't even make sense. Yikes. How did that happen? Before we had a solution that worked. But now... This is if we don't use it. Is this right? This should be right. Yeah, okay. Well, I mean, it's maybe more, right? But sorry, friends, this is a long video. I kind of knew this was going to happen, but this is a hard problem. But I feel like I was close, but then my next thing is not working. Index is the next index that contains the same thing. So this should be good. This should be good. This is using it. I think this. No, I mean this is just a for loop compression, right? If I get rid of the for loop should be good. Why? I mean it terminates, so I don't think this is going to give me anything. All I do is just caching what that is, that for loop. Yeah, and this should be good. Wow. And because this is big, it just means that we're doing some really weird thing. Don't even know how that can be this big, to be honest. What is that? 1707. Like, what is the square root of that? Is 248. That doesn't even make sense. So my math is just really off somewhere. End the series here. How does this even happen? Is this the -1 because -1 is something funky? Well, we had something that was right, but then now it's not. Next index, okay. That sounds like it should be good, but I don't know. Just want to see what happens. So that's still like really awkwardly wrong. It gets the wrong answer very fast though, which is good. How though? How does it get a number that big? I think that's the question I want to know. Because even 100 square doesn't get that big, so something else is a little bit wrong here. And this is ignoring it. Okay. This is keeping it. This is the worst. How do I get this ridiculous number? That doesn't even make sense. Is there anything in this input that is just this like big giant randomness? Like I get it could be wrong, but why is it, this isn't even like possibly wrong in a good way. Alright, well let's just print it out then. Sometimes I just have to do the hard things. Even though I was so close, I feel like we got the right answer with the for loop. So this is just making it n cubed, but then something is off by a little bit. Like how? Okay. So the O and did I have a, oops. How did I scroll up? Okay. Like, do I have some weird order of precedence thing? Why would it even, that would be funny if that's it, but I don't think so. Like, how does this combine like this? Should be another 30. So 0, 4, is there 0, 4? This is so very long. I don't get it. So 5, 8 after 2 count. It's gonna give us this ridiculous number, but how? Where? How does this combine stuff like this? This is just adding, right? I have a, like, how? This should be, oh, this shouldn't be O and 4. It should be 1, 1, 4. What is 1, 4? 1, 4, 0. No? That's very weird that it has 582. But with a 2 count, which is just 281. With a 1. Okay, so then now it goes to the first 2, has a 1, and then it just takes 1. Okay, fine, maybe. And that means that 3, 4? 3, 4. Yeah, okay. Why is 340 is equal to this thing? Dun dun dun. The plot thickens. Do I multiply something wrong by accident? Huh. Index, we don't. Only way that we have scores here. Print go of, was it 340? Is that what we said? This is going to give us like some out of bounds error. Okay, fine. Also, the sad thing is that I actually got rid of a lot of our test cases. I was going to paste it somewhere, but I forgot. Oh well, it's fine. Whoopsie daisies. Why? Was it 3, 4, 0, 1, 2, 3, and 4? Why is that returning 29,000 as the answer? Let's see. Oh, okay. I am dumb. Okay. Is this and also index is less than and? Oh my. Oh my. Oh my. Okay, I am dumb. I actually was thinking about that, but I forgot at some point because this has been way terrible. Okay, let's actually at least paste this one in. And then if this looks good, I'm going to give it a quick submit. Invalid test cases. Whoops. Really? Oh, whoops. This is why we want them. Okay. Oh no, this is wrong again. What? Didn't we get this one right before? Did I write off by one? Oh. Now I wish I have all my test cases because. I think this thing is not doing enough where we don't do anything. Yeah, I see. Because this is not doing this correctly. This is not doing the skip correctly. Because basically we want to get the score of everything in between. Basically we want to do something like this, but we don't want to do something like that. Because that will increase space. Okay. Okay. So that's why we do it this way, but then now it doesn't calculate the insights in the future in an easy way. So, can we do this compression? I thought we could, but then I think I forgot a case. I mean, this is the same as the for loop, though. Maybe I just misread and I thought they were correct. No, because on the for loop, what I did was that I had this as the left. Or something like that. That doesn't make sense. Maybe I just was. Maybe I misread it on the for loop. How do we express not doing it? Yeah, maybe I don't know. I thought I was close, but I was wrong. I thought we had this though. Yeah. Let me bring the for loop back. Oh, so okay. Let's just double check that we're getting back to the correct code. Okay, so now this is correct. And what I had was, so return, that's what I had. And I thought this part was good. That didn't really make sense that this should be good. Yeah, I don't think that this makes sense otherwise. Okay. Because we basically need, so we need the for loop. How do I compress this code? So this code is right, but it's n to the fourth. Or is that fast enough? I don't know. Well, this is a whole 1 second already. So we probably need to be faster. It's this part that we have to figure out. And that part is maybe non-linear. I mean, so we have a working n to the fourth solution, which we did probably like 10-20 minutes ago. But how do we compress this? What about the not case? The not case. Can I look at it backwards? Because now we're doing a chunk. No, because it's still a loop. And you need the entire chunk. This was always my arch nemesis, and this really showed. Even though I have all the tools, I'm still struggling with this. Unless the answer is n to the fourth, then I'm just kind of annoyed. But I don't know. Yeah. Okay. Maybe I don't. So the thing with this one is that I don't know if I could prove that n to the fourth is too slow. So let's just give it a try, and see how the test cases matches up. I don't know if there's an n cube solution. I think maybe that's the reason why I'm. Okay, so maybe I was wrong. Let's kind of take a look at. Let's see if I can learn something here, because this is n to the fourth for sure, and it's a little bit on the slower side. But what is the n cube solution? Let's take a look. Let's see. Take a look at the discussions. Hang on. And also how I feel like I probably have done this one, but that's the thing, right? Is that 100 million is a huge number in Python, so I wasn't able to. So I guess you can make some argument about that it's actually 100 million over 6, so maybe 7 seconds, right? So that's a pretty long time. And actually, I did it in C 2 years ago, 2.5 years ago. How did I do it that time? I guess I did it n to the fourth as well. Huh. So I did n to the fourth. Is there an n cube way of doing this? Let's see, let's just put on one solution. Nope, this is n to the fourth. Okay, so I mean, I guess I just actually had gotten this, but I just thought it was going to be n cube, or I thought there would be an n cube solution, because the thing is that with 100 to the fourth is 100 million, even though it's technically n choose 3 maybe-ish, so it's actually closer to 16 million, so maybe I didn't think about the math that way. But the timing is so tight that it's kind of hard to be confident about it, which is why I was thinking about an n cube solution for a long time. But yeah, this is a very long video, so I'm probably going to redo the explanations in the beginning anyway. But yeah, but I skipped ahead with the caching a little bit. But you can think about, like, in this case, left, right, and count can be from 0 to n. So this is going to be O of n cubed possible inputs. The number of states is going to be, which is number of states, and O of 1 per member per input space. So you got O of n cubed space. For time, it's going to be O of n time per input. So it's going to be O of n to the fourth time. That's all I have for this one. I don't know. I don't think I did the visualization very well, and this was a very long video. So yeah, let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a great Saturday. Have a great rest of the weekend. I'll see you later. To good mental health. Bye-bye.